In this video, we're going to look at the idea of evaluating polynomials at particular elements inside the ring of coefficients. To get started, we're going to need to let R be a ring, and we're going to let P of x be any element in the ring of polynomials where the coefficients are drawn from the ring R. Now, what this means, of course, is that P of x can be written as a sub 0 plus a1 times x all the way up to plus an times x to the n, or we could use sigma notation and write it as the sum as I goes from 0 to n of a sub I times x to the I. Now, I want to let alpha be an element of the ring R. In other words, alpha is in the same ring as the coefficients of our polynomial are. And we're going to define P of alpha to simply be replacing each one of these x's with the value alpha. So this is going to be a sub 0 plus a1 alpha plus all the way up to an times alpha to the n. Or in sigma notation, it's going to be the sum as I goes from 0 to n of a sub I times alpha to the I. Basically what this is that P of alpha is really capturing the idea of evaluate P of x at the value alpha inside my ring. And I want to make a note that P of alpha does indeed belong to the ring R, and that's pretty easy to see because each one of these products is something that is a product of things in R because all of the coefficients are in R and alpha is in R, and a sum of things that all belong to R has to be inside R by the closure of addition. So P of alpha is always in R, even though P of x does not belong to R, since x itself does not belong to R. So there's a distinction between where P of x lives and where P of alpha lives. Well, let's see. What's the next thing that I want to look at? Well, I want to actually see how evaluation works with polynomial arithmetic. So let's look at the following idea. I'm going to let Q of x also be inside R square bracket x. So Q of x can be thought of as b sub 0 plus b1 times x all the way up to, I don't know, bm times x to the m. In sigma notation, this would be the sum as I goes from 0 to m of b sub I times x to the I. Now, if I let f be the sum of p and q, I know how to write that, except that I don't really know whether m or n is the bigger of the two values. So I kind of want to think about how I want to write this. Well, P is the sum as I goes from 0 to n of a sub I times x to the I, and Q is this sum, I goes from 0 to m of b sub I times x to the I, and as long as I'm in the range where I'm less than or equal to the smaller of these two values, of n and m, I know exactly what to do. I'm going to be thinking about this as being nothing more than the sum as I goes from 0 to somewhere of ai plus bi times x to the I. But now we've got those leftover terms. Suppose this one is bigger, then I've got some bi's that don't have an ai to add to. But if this is bigger, then I've got some leftover i's. So the way I'm going to write this is that I need to go to the maximum of n and m, and I'm also going to define that a sub I is going to be 0 if I is bigger than the biggest of my actual legitimate a's, and b sub I is going to be 0 if I gets bigger than the degree of q. And let me make that notation just a little bit clearer. And now what I want to do is I want to think about evaluating f at alpha. So let's make this note. F evaluated at alpha is just going to be plug in alpha for the x in this expression. So we have ai plus bi times alpha to the I. But I can break that sum apart, and it's going to be the sum as I goes from 0 to the maximum of n and m of ai times alpha to the I, plus the sum as I goes from 0 to the maximum of n and m of bi times alpha to the I. But because we have these two facts here, once we get bigger than the degree of p, all of these a's are just going to be 0. So this is really nothing more than the sum as I goes from 0 to n of ai times alpha to the I. And the same thing happens over here. Once we get bigger than m, all of the bi's are going to be 0. So that sum is actually just going to be the sum as I goes from 0 to m of bi times alpha I. And what we now have is that this is nothing more than p evaluated at alpha plus q evaluated at alpha. In other words, evaluating sums of polynomials is pretty easy, and I want to kind of state that at the bottom of this page. So if f of x is equal to p of x plus q of x, no surprise, then f of alpha is going to be p of alpha plus q of alpha. Well, let's look at what happens with polynomial products as well. So let's now let g of x be the product p of x times q of x. Now, we already know that g of x is a polynomial of degree n plus m, and that means that it happens to be a polynomial that can be written as c0 plus c1 times x all the way up to plus cn plus m times x to the n plus m. And we know something from the previous video. From the previous video, we know that the coefficients of this product polynomial can be written as a sum as k goes from 0 to I of ak times b to the I minus k, where we do need the provision that ak is equal to 0 if we are looking at a k that is bigger than n, and bi minus k is equal to 0 if I minus k is bigger than m. In other words, we know that g of x, which is symbolically p, which is I goes from 0 to n of ai times x to the I, times q, which is the series as I goes from 0 to m of bi times x to the I. We know that this can also be written as the series as I goes from 0 to n plus m of, and I want to put this in a different color, the coefficient itself is the series as k goes from 0 to I of ak times b to the I minus k times x to the I. Well, now let's look at how evaluation works for this product polynomial. G of alpha, on the one hand, is going to have to be this, because all I'm doing to evaluate g at alpha is I'm plugging in alpha for the x's. So we have this mess, and we have, let's make that sigma a little bit nicer. This mess, and let me make that top much more clear. This happens to be P evaluated at alpha, and that is Q evaluated at alpha. But we also know that G of x can be expressed this way. So G of alpha can also be written as the sum as I goes from 0 to n plus m of the sum as k goes from 0 to I of ak times bi minus k, and then we're going to substitute in for that alpha, for that x to the I, alpha to the I. And if I want to think about what we've got here, what I've now got is that g of alpha is certainly going to be equal to p evaluated at alpha times q evaluated at alpha, but it can also, I mean, this part here really is g evaluated at alpha. And what I now am thinking is that evaluation certainly looks like it has the property of preserving both addition and multiplication of polynomials. In other words, evaluation at a particular alpha inside the ring of coefficients seems to look like it preserves ring addition and ring multiplication. In other words, it is certainly looking like a ring homomorphism. So that brings up the idea of the following theorem. So a theorem. Let's let R be a ring, and we are going to let P of x, we'll let P of x and Q of x be inside the ring of polynomials. We're going to define a map phi sub alpha that is going to take, so I need to make my notation look better. Phi of alpha is going to map the ring of polynomials into the ring of coefficients, and it's going to be given by phi of alpha applied to any polynomial is just going to be p evaluated at alpha. So up here I really should add to my theorem that alpha is going to be from the ring of coefficients. So let's get that up there. Now it turns out that, that if we define this map this way, then phi of alpha is indeed a ring homomorphism. Now I do want to look at the proof of this. And by the way, I want to introduce a piece of vocabulary. We're going to call phi sub alpha, the evaluate at alpha map. In other words, it's the evaluation map for x equal alpha. That's another way of thinking about it. Now, our proof that phi sub alpha is a ring homomorphism, we've actually already done all of the hard work. So I want to basically remember that. If I set f of x equal to p of x plus q of x, we've already seen, so we already know f of alpha is equal to p of alpha plus q of alpha. And just to formalize this, that lets us say that phi of this sum will equal phi sub alpha of f of x But that'll equal f of alpha, and we already know that f of alpha is p of alpha plus q of alpha. But that's phi alpha of p plus phi sub alpha of q. And now we simply have to do the same thing for ring multiplication. So again, what I want to remind myself is that if I set g of x equal to p of x times q of x, then we've already know, because we've already looked at it, that g of alpha is equal to p of alpha times q of alpha. And we can use this fact to then say the following. Phi sub alpha of this product, let me make my x's look like x's, that's just going to be phi alpha of g of x. Well, phi says to evaluate g at alpha, so that's g of alpha, but we've already seen that that is p of alpha times q of alpha, and that will be phi of p of x times phi of q of x. And so we really do have phi sub alpha taking r of x into r is a ring homomorphism. Now, just a little bit of vocabulary to tie this video up. We call phi sub alpha an evaluation homomorphism from the ring of polynomials to the ring of coefficients. And the other thing that I want to make a note of is that we get a different phi sub alpha for each and every alpha inside the ring of coefficients. So there are lots of these evaluation homomorphisms running around. There's one for each element of the ring R. And that ends this video.